Part 3 is concerned with design integration. The content of Part 3 is the following. First, we discuss generic design principles, which are advocated by various system thinkers of the ideal design school. Then we are discussing additional biomatrix design principles and considerations, such as the need for coherence of the 7 forces of system organization, the different emphasis in activity versus entity system design, strategic versus operational considerations in design, and then whole versus non-whole and whole versus parts and the implication of this in design, and sub-optimization. There are some generic principles which need to be considered when we do an ideal design. The different proponents of the ideal design school have come up with different principles which we have partly incorporated as well as added our own. Where all ideal design practitioners agree is that the design should be based on ideals. As we have heard, ideals are not achievable, but they are approximatable, and they can be reinterpreted in different ways in different or a changing environment. Also, an ideal design should transform the current system. That means it should be related to the current system, but in a transformative manner. Sometimes when one, as a management consultant, one works in a system and one has inspired people to work with designs, a participant can go a little bit overboard and lose the relation to the current system. So, for example, if I would work with an unhappy marriage, then the ideal design would not be related to the health of the persons involved, but it would have to stick to the relationship of the marriage. In other words, the current system is the marriage, and the ideal design must relate to the marriage. Another principle is that the ideal design should be realistic. This is put in inverted commas because we said early on it must be idealistic. By realistic we mean that we must make a design that is approximatable. For example, in one group I worked with at one stage, the issue was a traffic jam and how to make an ideal design for traffic. And one of the ideas that people threw up were we take helicopters to take out the cars in the blockage, in the traffic jam. Well, this is not realistic. The effort of resources stands in no relation to the benefit that the design can achieve. Or if I make a communication design and I say, well, we communicate by means of telepathy, this is also not a realistic design because telepathy is not the state of development of our brain-mind functioning to the extent that we can run systems on it. Another principle would be that the system must be a coherent whole. If you're sticking to the design frameworks that we provide in our programs and courses, that will happen automatically. If not, if one forgets an important aspect of a system, then I'm not creating a coherent whole and the design will not function. So if my framework is multidimensionality and I happen to forget the economic dimension, then the system will not function optimally. Or if my framework is the 7 forces and I forget the structure or I forget the governance, then the system will not be functioning appropriately. It will not be a coherent whole. One principle which all systems practitioners of the ideal design school agree with is that the system that is being redesigned must be capable of learning and development. It must be able to adapt itself to a changing environment in a creative manner. What is also important is that in doing an ideal design, the interests of the stakeholders of the design must be incorporated, or even more ideally, they should participate in the creation of the design. Another principle of how to create an ideal design is that it is typically involving an iterative process. One starts with a design and then other perspectives are added, the design is amended until all stakeholders involved are happy with it and are aligned around the design. If you have a design which is not acceptable to all stakeholders, it will in practice not work very well, if at all. If you create an ideal design, what is very important is that we look at the coherence of the 7 forces between them. In changing a system, one needs to consider each of the 7 forces of system organization, and they need to be coherent with each other. Why is that important? Well, if forces contradict each other, there will be conflict within the system. There could also be chaos without the system. So either the system is too rigid or the system falls apart. For example, if I have an ethos that is very learning orientated and creativity orientated, and I have rigid structures and procedures that forbid to do anything new, we have an inherent conflict. So whatever wins will destroy or threaten the other part of the system. So the 7 forces must reinforce each other in such a way that the system is stable but nevertheless can change. We are talking here about the ideal balancing between change and stability. So when we do a systemic organization transformation, we wire the organization for ongoing change. What that means is we have stable channels that channel information coherently and optimally into all parts of the system, but the water of creativity, the water of change that flows within those channels can continually be different according to the changing environment. And in this way we can achieve stability and order, as well as continuous change and to a certain extent internal disorder. So how do we do this? How do we create that coherence between the 7 forces? By means of a systemic organization transformation. This transformation must establish the necessary structures for channeling the change. The analogy of the riverbed comes to mind. This is not only the organization structure, but also the templates of knowledge management that embed the procedures in a structured way. And then we need to have procedures that ensure that change is continuously considered, that we know what is changing in the environment, that we know how the system should adapt to it, that we learn from how we behaved in the past and what the implications of that were. And all this is recorded within the channels of those knowledge repositories and is channeled by our procedures of ongoing learning, of strategic performance management, of various governance procedures. To create such a coherent design means that we need to apply system theory in the design of the transformation, but also that we manage the transformation systemically. This will be part of the module on systemic change management. Because if we are not taking the different parts of the organization along, if we are changing the system without those parts knowing about it or understanding the changes, we will not be able to create coherence in the system.
We have outlined briefly which of the 7 forces of system organization we emphasize in the context of an entity system and which we emphasize in a context of an activity system. I would like to elaborate a little bit on this in the context of making a design. We have in the introduction also talked about that the entity system represents a knot-like structure in the biomatrix, while the activity system is a string-like structure. And this analogy of knot and string already highlights or symbolizes how these different types of systems are organized. In the case of the entity system, I said we emphasize the structure, the coordinating governance, and the ethos of the system. The structure is built on the business function of the organization, so the matrix unfolds on the basis of the business functions of the system. And all activities flow within those matrix structure, all performance flows, all information flows, all governance flows within the matrix. The coordinating governance is the higher order governance that governs the interaction of the matrix, that makes sure that every activity system within the matrix adheres to those overarching rules that hold the entity system together. Very important is the ethos field, which sits at the core of the entity system and represents itself and its essence. It's that field of values and beliefs that is responsible for the unfolding of the entity system, the development of the entity system. It also gives rise to the overarching aims of the entity system, namely its reason for existence, its mission. The substance, the meta-energy information aspect, flows within each of the activity systems. And it represents the configuration of the structure of each activity system, as we have learned. Concerning the environment, the entity system is connected to the environment via each of its activity systems. So, in other words, it has a multidimensional interaction with its environment. One can see the entity system as a web within the web of the biomatrix. In designing an activity system, we start with the aim. As we said before, we depict the activity system as an arrow, so the aim represents the tip of the arrow. We have also said before that the overarching purpose of an activity system is very often inherent in its name, like, for example, an education system, a marketing system, a nutrition system, a parenting system, etc. Those names already depict the overarching purpose of the system. Once we have specified that purpose some more and determined some specific outcomes that we want to achieve, we also look at the process that we need to have in order to achieve those outcomes. Process was defined as the flow and transformation of substance or meta-energy information. Each time we have a transformation of MEI, we have a new input that needs to be processed into an output, and we have also achieved a new value. That is why we call an activity system also a supply chain of MEI and a value chain, the achievement of value along the way. The process and structure of an activity system are very closely interrelated. The structure is defined as the configuration of a substance that does the acting and that supports the processing. So the efficiency of the process depends on the way the structure is configured. We have used the analogy of the river to illustrate the difference between process and structure. The water in the river would represent process, while the riverbed represents the structure. The governance that we have to design must ensure that the flow of processing is actually achieving the outcomes. So, by analogy, our regulating governance would be concerned with digging the right riverbed and ensuring that the right amount of water is flowing in the system. In other words, the regulatory governance drives the performance of the system. It involves feedback, feed-forward, monitoring, evaluation, etc. The performance management cycle of we plan the aims and then we decide the activities we want to take, we implement them, we evaluate the outcomes, and we change, if necessary, our activities is what we refer to as the regulatory governance or performance management in an organization. Ethos is also important in an activity system. Activity systems typically have a function-specific ethos. For example, if our entity system produces cars, or I compare it to an entity system that produces shoes, the finance system of these two organizations will have a very similar financial ethos, a function-specific ethos. However, the function-specific ethos is also influenced by the entity system of origin of that activity system, in other words, the organization within which the finance system is operating. And it will also be governed by the client system, the systems that are being served by that function. Concerning the environment force of an activity system has its own function-specific environment. So there would be the financial environment or the environment of the education system. Typically, one looks at the upstream and the downstream, the supplier-related and the customer-related aspect of the environment, as well as the overarching industry environment. In summary, all 7 forces of system organization are important to both an entity and an activity system. However, the starting point in entity system and activity system design is different. And there is always an iteration between the 7 forces in designing an entity or an activity system. Another biomatrix design consideration is that of a different emphasis of the 7 forces in the context of strategic and operational design. We have learned that systems have a conceptual reality and a physical reality. So if we look at the 7 forces of organization, then the ethos, aims, and governance are the 3 forces that shape the conceptual reality of the system. We also call that the strategic perspective. They guide the overarching development of the system. The operational perspective that shapes the physical reality of the system is concerned with the flow and configuration of substance within process and structure. So this is where the real physical stuff in the system happens. Why is that important from the perspective of a design? Sometimes when we have to redesign a system and we look at the existing system, we find that its ethos, its aims are very good, but our processes and structures are so that we are not achieving those aims according to that ethos. In other words, our strategic perspective is okay, but our operational perspective needs to be relooked. Maybe we need to restructure the system, either activity system, a process system redesign, or in the case of an entity system, an organizational restructuring according to a three-dimensional matrix. And we need to look at maybe process efficiencies, etc. So not always when we are confronted with a design or a redesign situation do we need to redesign both the strategic and the operational perspective. Typically, we need to refine both of them and align both of them. But a complete restructuring or rethinking is sometimes only on either the strategic perspective or the operational perspective. Another biomatrix design consideration is the distinction between what is a whole and what is not a whole. We have discussed that to some extent in Module 1, that biomatrix system theory is a holistic theory because it clearly defines what is a whole and what is not a whole. More specifically, an activity system and an entity system are a whole. They are also systems in that they behave systemically according to the rules and principles of system thinking. System thinkers also work with other systems that are not wholes. They are typically issues or problems, systemic or complex problems, as for example poverty or climate change. So such issues would be spanning different kinds of wholes associated with nature and social systems, and can be depicted as spreading across, for example, the web of the biomatrix. So that blob, that grey blob within the web of the biomatrix could be an issue like poverty or climate change. System thinkers model that as a system, typically as a systems dynamics model, and they're looking to identify different variables associated with different natural or social systems that interact to create this emergent system. Of course, we can also have similar emergent problems or issues within an activity system, or complex organizational problems within or around an organization. These kind of systems are not wholes. In other words, a whole is a system, but not every system is a whole. The relevance of this is that if we're dealing with a system that is an emergent problem like poverty or climate change, we can only solve an issue like that by redesigning the relevant stakeholder activity and entity systems to behave in a different manner and interact in a different manner, so that they do not give rise to that problem of poverty or climate change. And through the different behavior, the problem over time gets dissolved. Another biomatrix design consideration is the distinction between a whole and its part. What is a whole? What is a part? We have defined that both entity systems and an activity system is a whole in its own right. However, we have also learned that entity system consists of activity systems. In fact, they emerge from the interaction of activity systems. Put differently, the activity systems of an entity systems are the parts of the entity system. So an entity like an organization has different parts, functional systems, business support system, organizational systems, etc. And those are the parts of the organization. What is the relevance of this? The relevance is that if I am fundamentally changing the entity system, it is likely that I also have to change all or some of its activity system parts. So if we do an organization transformation, it is very likely that afterwards some or each of the functions of the organization need to also review themselves and, if necessary, change or even transform themselves. Another important relevance of that is that most entity system, or often an entity system, has reasonable power over influencing and enforcing a change in its parts or in its activity systems. So if we are starting an organization transformation and it will be necessary to have changes in activity systems as well, the organization has reasonable power to enforce that its activity systems comply with those changes and transform themselves. Obviously, there is no full control over that, as they need the participation of the activity system, but they have reasonable influence to enforce it. Another important design consideration is that entity systems can be part of activity systems. For example, the staff of a production system are the entity systems that are participating in that particular production activity system. Typically, it is not all the functions of the entity system that are contributing, but only the relevant so-called business function that participates in the activity system. Likewise, in the body, if we are looking at a system like the circulatory system, then the blood cells participate in that system. The cells are the entity system that participate in the circulatory system of the body, which is an activity system. A problem arises if the entity systems are starting to do their own thing, are not guided by the overarching activity system and serving the aims of the overarching activity system, but start to serve their own aims. By analogy, if this is happening in the body, we are, for example, getting cancer, because the cells do their own thing, and what will suffer is the function of the body, and eventually the body, and with the body also the cells will die. We have a similar situation in society. If we have a societal function like an energy supply chain whose function is to provide energy to the members of society, we have different organizations, different entity systems associated with this overarching activity system. If those entities are self-serving and not interested in serving the larger activity system or getting their cues for functioning from the larger overarching activity system, then we will get problems analogous to the cancer. We will get an unsustainable energy situation, which in fact we have. And the reason why we do have unsustainable industries is because the entity systems associated with those industries do their own thing. They are self-serving, and they are perpetuating their own interests instead of participating in a larger collective interest. We have a cancerous society. The relevance of this is that we have to design public policy and do industry redesign to look at an industry as a coherent whole, so that the different parts of it, the different sections or sub-industries and the organizations associated with them can redesign their business models accordingly. Another important design consideration is that of sub-optimization and its connection to unsustainability. We have learned that optimizing the part leads to sub-optimizing the whole. Now, if we are looking at the organizational perspective, then optimizing the parts, any one of the functions of the organization, for example, is likely to sub-optimize other parts and the organization as a whole. We have given according examples. For example, if we optimize the production function, it is possible that we sub-optimize the sales and marketing function, or vice versa. If we optimize the sales function and we want to maximize our sales, it could be that the production function cannot cope. In both cases, the organization as a whole becomes suboptimal. In the public domain, we have a different situation. We have an optimization of the parts of an industry, of the entity systems associated with it. And as a result, we have a suboptimal activity system or industry. And this is the core reason for the unsustainable situation we have in the world. So as we optimize the individual organizations along a supply chain and optimize their interest, we sub-optimize the functional interest of society as a whole, and of course that of the planet. Reflections on system design. To summarize this module, let us do some high-level reflection on system design. We have learned that there are only two types of systems in the biomatrix. The string-like activity system, which is organized as a supply chain, and the knot-like entity system, which is organized as a matrix. Both types of systems are co-produced by the 7 forces of system organization, which we learned in more detail about in this module. In fact, the same design principles apply to all activity systems and all entity systems. Thus, in theory, there is no difference between making a design for the different types of activity systems. For example, there's no difference in principle and in theory between redesigning an industry and making a project design for my house renovation. Likewise, in theory and according to principles, there's no difference between the redesign of different types of entity systems, be they my neighborhood shop or a multinational or a public-private partnership. We could use music as an analogy to explain what we mean by saying that in theory there's no difference between the different types of system designs. Once we have learned how to play an instrument, how to read music, and we have applied this to learning to play a melody, then we know how to play that instrument. There's, in theory, no difference between playing that particular melody and playing a more complicated sonata. The difference is not in the way the music is applied, the difference is in the complexity of the music and my ability to play the instrument. In praxis, there is a considerable difference between the design of different types of systems. The difference lies, first of all, in the time horizon. If I am looking at the redesign of my home renovation, that may be a few weeks or a couple of months, while if we're redesigning an education system or the energy system of a country, we're talking time horizons of 40 to 50 years. That has its own complexity and its own considerations that are quite different from each other. Another difference is between current and future resource realities. In other words, the financial risks that are involved, environmental considerations that have to be dealt with, the scarcity of resources may be in the case of energy, or impacts on the environment. We also need to look at possible technological developments in future if we have a long time horizon that we have to deal with, and we need to incorporate some technological forecasting in our design efforts. Another source of difference will be the complexity in terms of the size of the system. The larger the system, the more amount of data need to be processed. There will be larger number of stakeholder groups and larger numbers of members of stakeholder groups. There will be greater difference in the types of stakeholders, etc. Different design exercises could also differ according to the number of iterations that they go through. There could be iterations between alternative designs. For example, one could have more or less renewable energy designs or different types of healthcare systems that one looks at. And there could be iteration between elements of these alternative designs. Then there could be iteration between wholes and parts. We could have an overall industry design, and as we cascade this into the sub-industries, we could learn about opportunities in a sub-industry that feeds back again and requires a review of the overall industry, etc. Then there could be iterations between sub-activity systems like a sub-industry and the entity systems or organizations associated with those sub-activity systems. We have previously given the example of the coal industry, that an activity system redesign or an industry system redesign of the energy industry could require from the coal industry to change its business model from continuous energy generation to complementary energy generation. This has implications for the organizations, the different coal organizations, and could lead to more design iterations. There could also be iterations between the design and the implementation plan. This is something we will discuss in the next module a little more in detail. Just an overview that we mention here, that we could find out in implementation planning that the design cannot be implemented, that there may not be enough resources around, so there will be an iteration back to the design demanding a review of the design, a design iteration. If we have alternative designs and we will have alternative implementation plans, there may be even more iterations between the different alternative designs and their possible implementation. A very fundamental difference between the design of different types of systems is the autonomy of the system and its parts. As we have mentioned in the introduction, if we are dealing with a whole, like a person or an organization that is relatively autonomous, and this whole wants to change one of its parts, it will be able to do so. For example, I can change my work life, or the way I do parenting, or my exercise regime, or I'm in charge of my own projects to a large extent. Likewise, an organization can change its different functions. It has a hiring and firing capability that allows it to have greater control about its change. By comparison, if we go into the societal domain, into the public domain, then we are dealing with a conglomeration of relatively autonomous parts that form a larger whole. Like we have independent or relative autonomous organizations that combine within an industry supply chain. There is currently a bottom-up causality that the industry emerges largely from the interaction of autonomous parts. If we want to redesign the industry as a whole, then we are dealing with that autonomy problem. We need the voluntary participation of different stakeholders. We have very little control over this. Of course, we have public policy and we have industry regulation, which to some extent drives that cooperation. To get this right is an overarching design challenge in the public domain. More specifically, we need to create a balance between the self-regulation of the autonomous wholes and the societal regulation of an overarching industry whole. On the one hand, we need to avoid the disadvantages to society from a rampant self-regulation, as we, for example, see in the current finance system, which leads to socialization of debts of banks and privatization of their profits and the indebtedness of whole nations. On the other hand, we want to avoid the trap of wrong societal regulation that leads to bureaucracy. A lot of it we see in the European Union, for example, or as we have experienced in the so-called communist societies during the industrial age. It is striking a balance between the different types of governance. We have to understand how form-maintaining, form-creating and form-destroying governance needs to be balanced in order to achieve balanced development between autonomous decision-making and societal decision-making. And we also need to look at the balance between contribution and distribution within society and the systems associated with them. Creating such balance is not only a design challenge, but it is also a challenge for change management in the public domain. And most importantly, as we have mentioned before, we need a change in the way public policy is made. From a shift from the current lobby-induced public policy to the design of public policy by all stakeholders. In other words, we need stakeholder co-design of public policy. Let us now look at design issues associated with the different types of social systems. Some of the most common problems associated with each of the 7 forces of system organization have been discussed in each of the sections of Part 2. There are, however, also generic design challenges associated with each type of social system that are related to the system as a whole and not so much to any of its parts or any of the forces that comprise the system. The overarching design challenge of a project is to create the most creative design that is possible within the available resources. Of course, it must be an implementable design. We will deal with implementation planning in the following module, and as we have mentioned before, there may be some design iteration required on the basis of implementation planning. The overarching design challenge of a function is to make a developmental contribution to the entity system it serves, not merely doing a competent job, which of course is the bottom line. In an organizational context, this implies how can my support service make a strategic contribution to the business of the organization and the organization as a whole? A typical example of this is how developments in the IT sector have actually changed the way business functions are being delivered by all sorts of businesses nowadays. The challenge of a business process system is to balance the short-term efficiency-driven goods and service delivery to clients with a long-term development orientation, development of all stakeholders, clients, organizations, as well as other stakeholders. The overarching design challenge of the industry is to design the industry as a coherent whole, to redesign the whole industry supply chain. The challenge of public policy design is to involve all stakeholder groups in the co-design of the policy. And the challenge of public governance is to regulate and govern the industry supply chain as a coherent whole, so that it benefits all stakeholders. The challenge of organization design is to create a coherent, three-dimensional learning matrix organization that is intimately connected with its environment. In fact, it is creating an organization that is a web within the larger web of the biomatrix. The challenge of a public-private partnership organization is first of all to create synergy between the partners in their goods and service delivery to a shared client, and also to develop other stakeholders. The other design challenge is to create the partnership as a coherent three-dimensional learning matrix. In summary, in facilitating a design of any type of social system, the designer should always bear in mind to design the system as a coherent whole, not a part system, always a whole. In doing so, the designer needs to remember that an autonomous whole can change its parts, but that a part alone cannot change its containing whole. This has, of course, change management implications. So if information about the various parts of a system are not there, it cannot be completely redesigned. Or if the different parts of the system should participate but are not available, we cannot redesign the system. This is the problem in open enrollment courses. As we have previously mentioned, if you're a member of an open course delivery and you work with a containing system, you are well aware by now that you cannot create an implementable design for the system because you lack the participation of the other parts. For this reason, we have designed the biomatrix transformation programs. They are specifically designed to involve different parts of a system to collectively co-design that system.